In part 4 of Module 5, we're going to be doing 2 examples to practice our understanding of the Carnot cycle and practice our understanding of the second law of thermodynamics. We're going to start with a simple example, and then we're going to continue with pretty comprehensive example that I think encompasses a little bit of everything that you need to know for Module 4 and 5 all together and sort of wraps everything together pretty well. So the first example is right here, and it says that an inventor claims to have developed a heat engine that receives 700 kilojoules of heat from a source at 500 Kelvin and produces 300 kilojoules of net work while rejecting the waste heat to a sink at 290 Kelvin. Is this a reasonable claim? Why? Okay, so the first thing I like to do in these cases is to draw the heat engine diagram and put all the information on the heat engine diagram. So let me draw this heat engine diagram on the left here. And so we have a TH that's at 500 Kelvin. And we're told that the QH coming in is 700 kilojoules. We have our heat engine in the middle. And our work produced is 300 kilojoules. And we're told we're rejecting heat into a sink at 290 Kelvin. So that's all the information that we're given. Okay, and from this information, we also know that we can find a lot of information from here. So we first of all have our two governing equations, which are work net is equal to QH minus QL. Okay, that's one of our equations that we have. If we want to find QL, we can. And the other equation is the thermal efficiency. So we can find the thermal efficiency of our system and see if it's a reasonable claim. So in order to check for a reasonable claim, what you have to check is if N thermal is less than or equal to N thermal reversible. That's what the question is asking. We're checking if the system that he claims he has invented is possible or not. So our N thermal for our system, we can just use work net over QH or Q in. Okay, so our work net over QH is going to be equal to 300 over 700, which is equal to 42.9%. So we know that his claimed engine makes 42.9% efficiency. And now we have to try and we have to try and compare it to our N thermal reversible. So we can use the equation for N thermal reversible and say that N thermal reversible is equal to 1 minus TL over TH. That would be the theoretical maximum based on the high temperature and low temperature given in our system. Okay, and if we plug that in, we have 1 minus 290 over 500, and we get that this is equal to 42%. So our theoretical maximum is 42%. Now we see that our thermal efficiency that the person has claimed or the inventor has claimed is higher than that. So we can say that N thermal is greater than N thermal reversible. And we had looked at this in part 3. We can say that his engine is impossible. There is no way that his engine can work between those temperatures and creating that amount of work from that amount of heat transfer. Okay, so very simple problem just to try and see if the claim of the inventor was reasonable or not, and clearly it was not reasonable. Okay, just a quick, simple problem. Now let's do a second problem with a commercial refrigerator. And this problem is going to take a little bit longer, but it encompasses a little bit from this module as well as the previous module, so I think it's a very good practice problem to understand and will help you to do your study problems as well. So we have we're told that we have a commercial refrigerator with refrigerant R134A as the working fluid is used to keep the refrigerated space at minus 35 degrees. Okay, so the first thing we can write is our system actually has a refrigerated space that's going to be connected to here that is at TL is equal to minus 35 degrees Celsius. Okay, and that refrigerated space is exchanging with the evaporator. Okay, that's the first thing to understand is that the refrigerated space is not inside the refrigerator. It's outside, and it's the part that is trying to be cooled by taking some heat out. Okay, and we're told that we keep the refrigerated space at 35 degrees by rejecting waste heat cooling to water that enters the condenser at 18 degrees and a rate of 0.25 kilograms per second and leaves at 26 degrees. So we seem to have a system, an open system here, where our condenser is, where our water is coming in and out and exchanging with the R134A. So the R134A is traveling through this system right here. Okay, so that's important to note. Then the refrigerant enters the condenser at 1.2 megapascals and 50 degrees. So we essentially have a heat exchanger here. This condenser is actually like a heat exchanger. It's a heat exchange between our water and our R134A. So we're told that the refrigerator enters the condenser at 1.2 megapascals and 50 degrees Celsius and leaves at the same pressure subcooled by 5 degrees. So subcooled by 5 degrees means that it's 5 degrees cooler than temperature of saturation. Okay, so we'll look at that in a little bit, but 5 degrees subcooled just means 5 degrees cooler than the temperature of saturation. Okay, if the compressor consumes 3.3 kilowatts of power, determine the mass flow rate of the refrigerant, the refrigeration load, the COP, and the minimum power input to the compressor for the same refrigeration load. So a lot of new information here that we have to process, but let's start first with a simple diagram of what we have and what our system gives us in terms of information. So what I like to do, as always, is to draw a system with our TH at the top, okay, and our TH is exchanging with QH, and we're going to do Q dot H. We're going to put everything in terms of Q dot because we do have power and we do have Q dot L as well in the diagram. So we have our refrigerator here, okay, and coming into our refrigerator, we're told that the work dot net is equal to 3.3 kilowatts, so we're given that information. And we're also given that Q dot L is here, and we have a TL that is equal to minus 35 degrees Celsius. Okay, so that's the information we're given in our problem. Now, the first part of the problem asks us to find the mass flow rate of the refrigerant. So we're asked to find M dot of refrigerant, or I'll call it M dot R, okay, for R134A. Now, in order to find the mass flow rate, what we can do is we can actually use our first law. So we're actually going to be using our first law. And we know we have a lot of information on the condenser system. So we have all the information of the water coming in, water coming out of the condenser, as well as the information for the refrigerant coming into the condenser and out of the condenser. So we can draw a little diagram of the heat exchange taking place within that system. So if we have the condenser, we can say that essentially the condenser is some sort of heat exchanger where we have one side coming in through here, coming out through there, This is the R134A. And we know the R134A is coming in at 1.2 megapascals and 50 degrees Celsius. And we know it's leaving at 1.2 megapascals, the same pressure, and 5 degrees subcooled. Which again, 5 degrees subcooled means under Tsat at pressure equals 1.2 in this case. Okay, so it means just 5 degrees under temperature of saturation at 1.2. Okay, it's just the way that they do it in the book. In a question in the exam, I wouldn't give you that 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 term. I would just tell you it's 41 degrees or it's 5 degrees under temperature of saturation. Okay, so I would give you the actual name of the temperature or a more clear explanation as to what's happening. So we have some R134A coming in and coming out. And then at the same time, within the condenser, we have some water coming in. And the water is coming in at 0.25 kilograms per second and 18 degrees Celsius and is leaving our system. It's leaving our system at 26 degrees. Now, what we notice is for water, we are not given pressure. And if we're not given pressure, it's going to be very hard to use our tables for the water. So we're just told water comes in at 18, leaves at 26. That's it. So we're not given pressure. And if we're not given pressure, we're going to have to make some assumptions. But we'll look at those assumptions in a second. Again, if you had this type of problem in an exam, I would probably give you some pressure of water so that you could use your tables for the water. But it's not always necessary, and it's not always the case, right? If you remember your problems where you had, for example, water and copper being mixed together, you would use Cp delta T in that case, which is what you could do here as well, or Cv delta T, whichever is useful for whatever problem. So we're going to do a first law analysis of this heat exchanger. So we've done heat exchangers before. We've looked at how the heat exchangers work, but essentially we can do first law on heat exchanger. And we know that heat is going from R134A to our water. Yes, to our water. The reason we know that is because water is coming in at 18 degrees and coming out at 26, and our R134A is actually doing the opposite. It's starting at a high temperature and going to a lower temperature. So that means there's some heat transfer in here between our R134A and our water. Okay, so we can solve our problem by looking at just the water system first. So let's look at the water side of the heat exchanger first. So if we look at the water side of the heat exchanger, we have the following. We have that Q dot H, which is Q in. Okay, so Q dot H is the actual Q going into the water. Okay, that's the water is exchanging with the R134A. The R134A is part of the system, so the Q dot H is actually the part that is exchanging with the water. So we have some Q dot H into the water minus, and let me write it in white, minus work dot out is equal to m dot times H2 of water minus H1 of water plus delta KE plus delta PE. And these go to 0 because we're not given any information on the velocity of the flow coming in. Now, if we had some velocity of the flow coming in, we could take into account our kinetic energy for sure. Okay, and we also know that work dot out goes to 0 because we just have some tubes and a heat exchanger. Nothing is moving. There's no moving parts. Okay, so if we look at the water system by itself, essentially what's happening is our water is coming into the condenser at 18 degrees, leaving at 26 degrees. Okay, so the water is going this way. And within the heat exchanger, there's some Q dot H from the R134A. Just isolating the system in itself. And if you look back at your example problems with some heat exchanger, you should be able to figure out why that is the case. So we have that Q dot H is equal to mass flow of water times H2 of water minus H1 of water. Okay, so we are left with this simple equation. Now, what do we use for H2 and H1 of water? Well, we're going to have to make some sort of assumption. We're going to have to try to make an assumption as to what is happening. So what we're going to say is that since water is between 18 to 26 degrees, we can assume that if the water is not under too little pressure, we know that usually at, let's say, a normal condition, we can assume the water is a compressed liquid. And since we assume that water is a compressed liquid, we can say that we can find HF at the given temperature. Okay, so if we find HF at given temperature, that would give us our H for the compressed liquid water, assuming that the pressure is not too high or the pressure is not too low where the water would actually be steam. But I think that we can make a safe assumption that we have a compressed liquid, and we're going to use our special rule that says find HF at a given T. We could also find VF and UF, but in this case, it's not going to be useful for our problem. Okay, so we're going to find HF. So we're going to find H1W, which is going to be at 18 degrees, and we're going to find H2W, which is at 26 degrees. The other way we could do this is just to say, let's use CP for water. So instead of finding the table values, we can find CP of water at the two temperature and use CP delta T. Either way is fine, but you'll see that with your tables, you might get a slightly more accurate value. So let's go to our tables and let's look at water, and let's look at our temperature table and find our HF for 18 degrees Celsius and HF for 26 degrees Celsius. So if we go to our tables, we can go to 18 degrees, and we can see that we obviously do not have 18 degrees, so we have to interpolate between these two values to get the H1W, and to get H2W, you would have to use 26 degrees, which again, you would have to interpolate between these two values right here. And by interpolation, if you actually do the interpolation, I'll let you do that by yourselves, you get that H1W, so from table A4, you get that H1W is equal to 75.74 kilojoules per kilogram, and H2W is equal to 109.01 kilojoules per kilogram. Okay, now once we have that, we can find our Q dot H. And our Q dot H is going to be important for the rest of the problem, but it's also going to be important to try and find our mass flow rate of our R134A. So we have the mass flow rate of water. The mass flow rate of water in the question is given as 0.25 multiplied by 109.01 minus 75.54 is equal to 8.367 kilowatts. Okay, so we have a heat transfer of 8.367 kilowatts in our system. Now that we have our Q dot H, we can now look at our system from the other side. We can look at our system in our heat exchanger from the side of the R134A. So the R134A, what it's doing is it's transferring heat out. Our Q dot H is coming out of R134A, going into the water. And we know that the R134A is coming in at 50 degrees Celsius, 1.2 megapascals, and is coming out at 1.2 megapascals, and again, 5 degrees subcooled, which we'll find in a second what that means. So now that we have this, what we're trying to find is the mass flow rate of R, or the mass flow rate of R134A. So once again, we can apply the first law. And let me just put like a separation here. So we're going to apply the first law. And the first law states Q in is equal to M dot R times H2 minus H1. So this time, our Q in is actually going to be negative Q dot H, right? If we think about it, if we have a Q in would just be the negative of Q dot H. So we have that Q in is equal to the negative of Q dot H. And so we have negative Q dot H is equal to M dot R multiplied by H2R minus H1R. And now that we have those two values, we just have to find H1 and H2. Once we have H1 and H2, we can find M dot R. We already have Q dot H. So for R1, we have P1, T1. So we have 50 degrees for 1.2 megapascals. We can go to our R134A tables to figure out our H1. So let's go to our tables. If we go to table A12, which is our pressure table for R134A, we would then go to 1.2 megapascals. At 1.2 megapascals, we see that our saturation temperature is 46.29. So that means that we are actually, so let me just write it out here. So we have 46.29. We can say that T is greater than Tsat. Therefore, we're going to go to superheated. And now that we go to superheated, we can go to 1.2 megapascals. And we see that at 1.2 megapascals, at a temperature of 50 degrees, we have that H is equal to 278.28. So we're going to write H1 is equal to 278.28 kilojoules per kilogram. We now are going to find P2 and T2. From P2 and T2, we're going to find H2R. P2 is 1.2 once again, and T2 is actually Tsat minus 5. And this Tsat minus 5, if we go back to our tables here, if we go to table A12 again, we see that Tsat is 46.29. So our subcooled by 5 degrees is just going to be 46.29 minus 5, which we can say is 41.29. Okay, and then from 41.29, we now know we have a compressed liquid because it's subcooled. Okay, so this is compressed liquid. So we're going to go to table A11 and interpolate to find. So we're going to interpolate to find H2R is essentially equal to HF at 41.29. So just to show you the process, I'm not going to do the interpolation, but just to show you the process, you would go to table A11. You know that your temperature is between 40 and 42 degrees. So between 40 and 42, we have 108.28 and 111.28. So it'd be somewhere in the middle there. And the value turns out to be H2R is equal to 110.19 kilojoules per kilogram. And so now we can find m dot r from this. So we have that m dot r is equal to minus q dot h, over 110.19 minus 278.28. And we get a mass flow rate of 0.0498 kilograms per second. Okay, so that's our value for the mass flow rate of refrigerant. So in part A of this problem, we only used the first law. And it was essentially a first law problem with an open system, so just like we did in Module 4. And now we can finally go to parts B, C, and D and use our knowledge of Carnot cycles and use our knowledge of the second law to solve the rest of the problem. So let's look at part B. So part B in the question asks for the refrigerant load. So the refrigerant load, and the refrigeration load. So what does the refrigeration load mean? So that's another thing in your book. Sometimes they ask you a question and they don't really tell you what the refrigerant load is. Even in your actual text, you don't really see it. But the refrigerant or the refrigeration load is Q dot L. Okay, so you can remember this, that the refrigeration load or the refrigerant load is Q dot L. And once again, in an exam or a test, I would not give you a question asking you for the refrigerant load, but I would actually tell you find the Q dot L, for example. Okay, so we have, how are we going to find Q dot L? Well, we already have Q dot H, and we already have work dot net given in the question. Q dot H we found from part A. So we can actually use the equation work dot net is equal to Q dot H minus Q dot L, and we can rearrange this to say Q dot L is equal to Q dot H minus work dot net, and that would be equal to 8.3 minus 3.3, and it's not 8.3 exactly, it's 8.367 or 8.37, so we get that this is equal to 5.07 kilowatts. So very simple, just a use of a simple equation that we know for our system. We don't have any information on if it's a Carnot or not. Obviously, it's not a Carnot engine. It's not a Carnot refrigerator. We're not told this is our theoretical maximum. We're just told this is an actual system. So we just use the regular equations to find our values. Now in part C, we have the following question. Part C asks us to find the COP. So for the coefficient of performance of refrigerator, once again, we're not told that it's a reversible refrigerator or anything like that. We just use our common equation for COP. So we have a few different versions of the equations, and you can use your formula sheet that has been posted to look at all the equations. But here we actually use the simplest equation, which is just Q dot L over work dot in. We have both of them. Work dot in is just work net. So we get that this is 5.07 over 3.3, which is equal to 1.54. In part D, we're asked to find the minimum power input to the compressor. So in the question, we're told, find the minimum power input to the compressor for the same refrigeration load. So we have the same refrigeration load. So this is our Q dot L. And we're told what is the minimum power input to the compressor that we would need. Okay, so how do we solve for this problem? So the minimum power is achieved in our system how? So we have to look at our equation for COP. So we know that COP is equal to Q dot L over work dot in. And we're told in the question that we cannot change Q dot L. So Q dot L does not change. So what is the minimum power that we can use? Well, the minimum power we can use is actually used if we have our maximum COP. So what we need to find here is our COP max for our system. If we find our COP max, it will mean that we have minimum power. So the less power you use, the more the COP. So we just need to find the maximum COP. That way we can work backwards and find our power minimum. So how do we do it? Well, this max COP of our system is actually equal to COP of refrigerator reversible. So it's COP of the reversible refrigerator or Carnot refrigerator. So we know that COP max is equal to 1 over TH over TL minus 1. And we have the temperatures of TH and TL. So TH, the temperature of TH is actually the temperature of the water coming into the heat exchanger. It's 18 degrees Celsius. That's the temperature of the water that's exchanging with our system. It's the temperature of the water coming in. So we have that this is 18 plus 273. Do not forget to change it to Kelvin. If you do not change the temperatures to Kelvin, you will get very, very strange results. The TL is given as minus 35 plus 273 minus 1. And so we get that the maximum COP is 4.49. So now we can actually check if our COP of our refrigerator made sense. Our COP of our refrigerator is 1.54. So we know that it's actually a possible refrigerator, okay? It means that it's below Carnot, so it makes sense. We have a lower COP. Everything is good on that side. So now let's find the power minimum. So the power minimum happens when we have our maximum COP. So we know that our power minimum is going to happen when COP max is essentially equal to Q dot L over work dot minimum. Okay, and so we're just going to rearrange the equation to find work dot min. So work dot min is just equal to Q dot L over the maximum COP of our system. That's going to give us the least amount of work to get to our maximum coefficient of performance. And we get that this is equal to 1.13 kilowatts. So if we put work at 1.13 kilowatts and we got the same Q dot out from our system, that means we would have the most efficient system possible. So this concludes our discussion of Chapter 6 and Module 5. And in Module 6, we're going to be discussing the second law from the perspective of entropy and trying to understand how we can quantify how far away from a reversible process we are mathematically. So we'll see you in Module 6.